Good evening. Good evening. I'd like to welcome you to the Simon Center for Geometry and Physics and to this edition of the Della Pietra Lecture Series. We're very pleased today to have Professor Robert Kirshner as our lecturer. Stand over here so I can read my notes. Professor Kirshner is the, I can't read my notes, it's dark over here. I know what, if I put on my glasses it'll work better. There we go. Professor Kirshner is the Clowes Professor of Science at Harvard University, a 1970 graduate of Harvard College. He received his PhD from Caltech and recently received an honorary degree of science from the University of Chicago. He served as president of the American Astronomical Society from 2003 to 2005. He's a member of the National Academy of Sciences and of the American Philosophical Society. He shared the 2007 Gruber Prize for Cosmology and received the 2011 Heineman Prize for Astrophysics from the American Institute of Physics. Two of the recipients of the 2011 Nobel Prize in Physics, Brian Schmidt and Adam Riess, were his graduate students at Harvard. He's a frequent public lecturer on astronomy. He teaches a large undergraduate general education course at Harvard called The Energetic Universe, and he is the author of a popular level book, The Extravagant Universe, Exploding Stars, Dark Energy, and the Accelerating Cosmos. And I believe maybe one of his principal reasons for coming here is to publicize that book and get more sales. So these list of accomplishments and honors indicate the important influence that Bob Kirshner and his work have had on the field of astronomy. They also indicate his ability to explain his field to general audiences such as this one. I look forward to an exciting and inspiring presentation. And with that, let us please welcome Bob Kirshner.
Thank you. Thank you. It's a pleasure to be here. This is such a special kind of an institution that seems to have really complicated art as well as interesting ideas. I saw the assistant to the sculptor of the big topological sculpture out in the plaza over there, who was inside the sculpture. And if I understand it correctly, if he goes around 3 times, he will be outside the sculpture. All right. What I want to talk about today is the history of the universe, in particular, the history of the expansion of the universe. We know, people have known since the 1930s, that we live in a universe where the galaxies are moving apart, and I'll show you the evidence for that. But what's new is that we've been able to make measurements over a large span of time with enough precision to see that that rate of expansion has been changing, and that the universe is expanding faster now than it was in the past. This is a big surprise because gravity works the other way. You know, you throw a ball up, it slows down. This is like throwing a ball up and having it take off and not come back. So it's a surprising thing, and you should be skeptical enough to ask, where is the evidence for this? Well, let me show you. Here's a galaxy. I'll show you that if you think about the universe, the thing to think about are the galaxies, how they are moving. But the galaxies are made up of stars, which in themselves are made up of atoms. The stars go through their ordinary lifetime, which is very long in most cases. But in a few cases, the star comes to a violent end. And this bright dot down here is one star in this galaxy, which has 100 billion stars, which for a little while, about a month, glows as brightly as 4 billion stars like the sun. This is a supernova explosion, which is the destruction of a star at the end of its life, a thermonuclear explosion. And it's by measuring the properties of these supernovae and the motions of the galaxies that we've been able to plot out the history of cosmic expansion, as I'll try to explain in the next 40 minutes. Now, if I'm going to really do this in 40 minutes, I have to leave out credit to a lot of other people, but you understand that they also did a lot of good work. But let's start with a technological point. I showed you that first picture. It was a Hubble Space Telescope image made with an electronic detector, with a charged coupled device, a silicon detector. That's not the first kind of technology used to measure the light from astronomical objects. Photography of the chemical kind, and the earliest one were daguerreotypes. So here's a daguerreotype of the moon made at the Harvard College Observatory. One interesting thing about photography that's different from looking through a telescope is that the detectors accumulate light over a period of time. That often allows you to see fainter things than you can see with your eye. And they make a durable record so you can take the data one time and study it another time. And in the case of photography, that led to a change in who could do the observing. Because you didn't have to be at the telescope, and you didn't have to be up at night. The director of the Harvard College Observatory recognized this and had kind of a industrial plan for how to use photography. He said, a great observatory should be as carefully organized and administered as a railroad. You might think about that for a mathematics institute. All right, great savings, he said, may be effectuated by employing unskilled and therefore inexpensive labor, of course, under careful supervision. What did he really mean by that? Well, turns out that Pickering had an assistant, and his assistant was a man who was not very good at being an astronomer's assistant. And one time Pickering got mad at him, and according to legend said, my housekeeper could do a better job than you. And so he hired his housekeeper and a large group of women. So here's his housekeeper, Wilhelmina Fleming, and these women from the local colleges, including Radcliffe and Wellesley and others in the Boston area, became the low-cost labor that he exploited in a way, but also allowed to get a start on doing astronomical research. So the fact that women who could never go to the telescope and stay up at all night, good heavens, but they were certainly in that time thought to be very good at handling these photographic plates, and Harvard had a lot of them at the time. So here are the Harvard computers, as they were called. That was the name of the job, being a computer. And this woman back here is Henrietta Leavitt, who plays an important role in this story of measuring the scale of the universe. She noticed that there was a particular kind of star, kind we called Cepheid variable stars, and that they had a property, which is that the brighter ones had longer periods of variation. So these are stars that got bright and dim again over a period of days or weeks. And what she found was, by measuring how long it took to get bright and dim, you could tell whether you were looking at an extra bright star, one of ordinary brightness, or one that was a little dim. The reason this is important is that that's one of the ways that we judge distance in astronomy, is by the brightness of objects. You know, if you sail a boat up the coast of New England, there are lots of lighthouses, and there are navigational books that will tell you, if you're traveling up the coast, do not try to judge the distance from the shore by the brightness of the light. But that's what we do in astronomy. We imagine that the sources are all the same brightness, that there is no fog, that there is nothing else going on, and try to measure the distance to objects by how bright they appear. And knowing how bright they really are, of course, is at the heart of that. Of course, if you're wrong in navigation, the penalty is shipwreck. If you're wrong in cosmology, the penalty is an addendum, erratum, maybe another paper, I don't know. Anyway, so those stars were used to measure the size of the Milky Way galaxy. This is not a picture of the Milky Way. We don't have a way to get out and take a look at it. But what we do know is that we're not at the middle of it. Stony Brook, the Earth, the Sun, and the stars that you see at night are in a patch in the Milky Way that is far from the center. Astronomical distances we usually reckon in a kind of funny set of units that are related to the speed of light and to time. The speed of light, which is sort of the metaphorical speed of really fast, is of course very slow for astronomical purposes. It's a foot a unit of distance used in the United States and Liberia, a foot in a nanosecond, a billionth of a second. So the speed of light is, in ordinary life, not something that we have to take into account. When I'm looking at the people in the front row, I see the light that bounced off them 10 nanoseconds ago. Curiously, the people in the back look younger because I see them as they were 100 nanoseconds ago. Okay, just a humorous remark in this room, but in the universe, this idea that you see nearby objects as they are and distant objects as they were makes a telescope a no-nonsense time machine that lets you see the light from the past, see what the universe was doing in the past, and, as we'll see, measure how the acceleration of the universe, the change of the expansion of the universe, has taken place over time. Okay, so we live on a planet. It's not the center of the universe. You knew that. The sun, turns out, is not the center of the Milky Way galaxy, and I'll come back to that idea later. Because you might ask, well, that may be true, but isn't our galaxy somehow the middle of the universe? And I'll show you the answer is probably no. Okay, what is the universe? Well, in 1916 and 17, when Albert Einstein was applying the theory of general relativity, the theory of gravity, to the universe as a whole, he consulted with astronomers, and they said, well, this is the universe. This thing, the Milky Way, the system that the sun is part of, is the thing in the universe. It's made up of stars, and the stars are not moving away or coming toward us on average. It was a static, kind of boring universe. However, the most important thing in this picture is that. That's the next galaxy out, the next big galaxy. That's M31, the Andromeda galaxy. These things were called spiral nebulae by Hubble and by others at his time, but it is the distances to those objects that give the clue that the Milky Way is not the only galaxy, is not the whole universe, but instead one of about 100 billion galaxies that make up the universe. So how did that story get going? Well, here's Einstein. And I want to emphasize the technology again. This is a photograph taken with ordinary photographic emulsion. So, you know, there's silver halide, silver salts in some kind of goo made out of horses' hooves, and it's spread on glass, and then light shines on it, and a chemist, you do something in the darkroom to turn it, you reduce it to turn it into silver metal. And it was very slow. That is, it took, the shutter had to be open for a long time in order to collect enough light for an indoor scene. So you can see that this guy behind Einstein was shaking his head no. He disagrees with Einstein. And the person in the chair next to Einstein got up and left while the shutter was open. Now, I bring that up because we'll see that the changes in technology for measuring light have really been important in this story. But there is another change in technology, which is we now can look at old photographs and find out what people were thinking. And what Einstein was thinking was that the universe must be static. By universe, they meant the Milky Way galaxy. Okay, so the story broke open by applying what Henrietta Leavitt had learned to these nebulae, to these distant spiral galaxies. And the place where those measurements were made were with this telescope, the 100-inch telescope at Mount Wilson. That's up behind Pasadena, overlooking the valley that has Los Angeles in it. A little village of 25,000 at the time when the telescope was built. The subsequent growth of the lights in Los Angeles have handicapped this telescope quite a bit. Nevertheless, it was built about the time of the Titanic, and by successfully avoiding icebergs, it's still in operation. The observer for this telescope that I'd like to talk about is Edwin Hubble. He's shown here wearing jodhpurs and very nice riding boots for the photographer, no doubt. Anyway, here he is looking through the eyepiece, and his job is just to keep the telescope tracking across the sky. It had a kind of clockwork mechanism while a photographic plate was being exposed. He was looking for stars that would change in M31, in that spiral nebula, to try to estimate its distance. And here's a picture that he took, a photograph that he took, This is from just 1923, just about this time of year when Andromeda is high in the sky. And Hubble marked on the glass side of the plate this N, that means it's a nova, he thought, a new star, here's a new star, and this one he thought was a new star. And then he changed his mind and put variable. This is the same kind of star that Henrietta Leavitt had seen in nearby systems, only it was hundreds of times fainter, which meant that the galaxy in which it was located was tens of times farther away. The brightness goes down like the square of the distance. So for a 100 times fainter supernova, 100 times fainter star, the distance would be 10 times as big. So this is outside the Milky Way. This is not part of the Milky Way. This is more or less equal to the Milky Way. So Hubble used the brightnesses of stars and galaxies to judge their distances. The spiral nebulae are not in the Milky Way. They are, however, in the operating system for Macs, as you may have noticed. If you've got a modern one, it has a picture of M31 when you open up the screen. Is that right? He's got a Mac back there. Anyway, I know it's right. Okay. Now, this is the evidence that the Milky Way is not the whole universe. It turns out all those galaxies out there are far from us, not part of the Milky Way, and it's galaxies all the way out. If you take as deep a picture as you can, and this is the picture which was in the New York Times today of what they call the extremely deep field taken with the Hubble Space Telescope, so that's been named after Edwin Hubble. It's about the size of the 100-inch telescope, but it's at a much better site, being not near Los Angeles, actually above the Earth's atmosphere in orbit. And this is a little tiny piece of the sky, smaller than the fingernail on your little finger. And what you can see are these blobs of light, each of which is a galaxy, each of which is a system of stars with 100 billion stars or so. And I'm not just talking about the big ones. I'm talking about the littlest, tiniest fleck that you can just barely make out in this picture. Those also are galaxies. And we think the universe has about 100 billion galaxies, more or less, like the Milky Way in it. Okay, so that's part of the story. Big universe, big distances. The other part is that the universe really isn't static. It really is in motion. And the way we know that is by taking the light from distant galaxies, spreading it out into a rainbow with a prism or a grating, and measuring the displacement of the lines due to the absorption or emission from different chemical elements in the stars of those galaxies. So first of all, we find that the stars in distant galaxies are made of the same atoms that we have here on the Earth. The only difference is that in general, we see that the lines, the absorption lines, are shifted to longer wavelengths, out toward the red end of the spectrum. So Slipher did this heroic work at the Lowell Observatory, used a small telescope, and exposed these photographic plates for night after night after night in order to measure this effect and see the velocities of these spiral nebulae. And what he found was also consistent with the idea that they were not part of the Milky Way. The velocities were much bigger than the velocities of any stars. What's more, they're almost all moving away from us. They're shifted toward the red end of the spectrum. So this gave astronomers two kinds of numbers: distances from Hubble, velocities from Slipher. Slipher's list was done in 1925. Hubble's distances were done in 1923 and 4 and 5. And Hubble didn't quite get around to plotting one thing against the other until late in 1928 and published it in 1929. If the speed of light were the speed of light is 1,000,000 times as fast as the speed of sound. So we hear effects that correspond to this stretching of light toward the red as the Doppler shift, as changes in the pitch of cars. So if a car is traveling 60 miles an hour, that's about 1/10 of the speed of sound. And so there's a net change as a car comes toward you and away from you in the wavelength and the frequency, the pitch that you hear. You know this. A car goes by. It changes from high pitch to low pitch as it passes you. If the speed of light were 1,000,000 times lower, highways would look like this. You know, cars that were going away from you would have red taillights, and cars that were coming toward you would have kind of blue, well, they do, but that is not the reason. It's not the reason. Nevertheless, it gives you the idea that you can measure from the properties of the light whether something's coming toward you or away from you. Now, in fact, there are devices that use the Doppler effect with light, with radar, as a matter of fact, to measure your speed. But they have to do that to a very high precision, a part in a billion, roughly, precision in order to stand up in court. I know this because I explained this to an officer of the law, and he said, "Tell it to the judge, Mr. Harvard professor." Anyway, my efforts at public education are unending. Okay, so here's this diagram where the distances that Hubble had measured are horizontal. The vertical axis is the velocity, and it says 500 kilometers a second, 1,000 kilometers a second. Those are much bigger. 1,000 kilometers a second is much bigger than the speed of stars in the Milky Way. And what you can see is not only are these things moving, preponderance of them moving away from us, the positive numbers means away, negative numbers means toward us. You can see there are just a few over here of objects that are below the zero line that are coming toward us. Most of them are moving away from us, and there's an interesting thing. You see this line here. The things that are more distant seem to be moving away from us more rapidly. More distant, more rapidly. This is Hubble's law that the velocity is proportional to the distance. The interpretation of that, which Hubble never really believed, is that we live in an expanding universe, as I'll try to convince you with some cheap graphic tricks. Okay, now at Harvard, all the tenured faculty and some of the undergraduates believe that this fact about the universe believes that is proof of something they've known since they were 3, namely that they personally are at the center of the universe. And so you can see here this vision of all the galaxies moving away from you. Now, I started out by saying you know that the Earth is not the center of the universe. I mentioned that the sun is not at the center of our galaxy. This would be a picture in which you somehow believed that our galaxy had a unique position in the center of the universe. Another possibility, which turns out is perfectly reasonable, is that everybody has the same view, a much more democratic view of the universe, in which everybody has the same view. It's just that the universe is stretching out in all directions, expanding. So here's a cheap graphic trick meant to persuade you or delude you into thinking that you understand this. The idea is we start with a galaxy, and here's a galaxy nearby, and what I've done is just push the enlarge button, and I've made these pictures bigger and bigger. And what you see is an object which was nearby moves a certain distance in that time, so it would have a speed away from you. But here's another object which was significantly farther away at the time when we started, and look, it moved a lot farther. This one only moved this far during that couple of seconds while the animation was underway. This one moved much farther. It started out farther away, and it moved faster. If you plot up, if you were willing to do the tedious job, maybe we could give it as a homework assignment. Maybe we could find some assiduous people who would work at low wage. Anyway, whoops, sorry. You'd see that the velocity is proportional to the distance in this picture. So that's the idea, that an expanding universe is the same as one in which we see Hubble's law, velocity proportional to distance. Maybe it will help another metaphor. Imagine, through the generosity of Mr. Simons, I was able to double the size of this room. Then what would you see? You'd see your neighbor, who's 1 seat away, would end up 2 seats away. But the person who's 10 seats away would end up 20 seats away in the same length of time. So you would see what everyone else would see, namely all your neighbors moving away from you and the more distant ones moving more rapidly. Okay, so that's the idea here. If you go to the NASA website, they have a really poor demonstration of this. They say, imagine you had a loaf of bread with raisins in it, and you were ruthlessly metric about measuring the distances in your loaf of bread, and as it would rise, all the raisins would see the other raisins moving away from it. And if you imagine a raisin making measurements of the Doppler shift and of the brightness of other raisins, well, you could imagine a little Hubble on one of those raisins. Oh, never mind. Okay, so the idea is that the universe is expanding, and the evidence is based on this relation between velocity and distance. It's also consistent with Einstein's theory. Einstein had put in by hand a constant, the so-called cosmological constant, which made a finely balanced static universe. But here he is visiting Mount Wilson. This is the library at 813 Santa Barbara Street in Pasadena. Here's Humason, who measured the redshifts for Hubble. Here's Hubble. Here's George Ellery Hale patting him on the head. Good job. And here's, of course, the visiting theorist. So Einstein had started out by saying, static universe, put in that cosmological constant. But by this time, the astronomical evidence was quite strong. And even though Hubble himself wasn't so sure about it, other people understood that this really was a universe that was changing its scale, changing its size with time. Einstein's original gravity equation was correct. This is from George Gamow, whose books I read in high school, and it sort of helped me get going on being a scientist. Anyway, he says Einstein's original gravity equation was correct, and changing it, that is, putting in this cosmological constant, was a mistake. Much later, when I was discussing cosmological problems with Einstein, a sentence I wanted to have in my book, much later, when I was discussing cosmological problems with Einstein, he remarked that the introduction of the cosmological term was the biggest blunder he ever made in his life. But this blunder, rejected by Einstein, is still sometimes used by cosmologists even today, and the cosmological constant denoted by the Greek letter lambda rears its ugly head again and again and again. Okay, George, calm down. Well, what I'm here to tell you this evening is that the evidence is that there's something like the cosmological constant that's making the universe speed up, that lambda, this Greek letter lambda, is rearing its ugly head again and again and again. So Einstein didn't like the cosmological constant after that. He said, let's get rid of it, not just set it to 0 and keep it in the equations, just leave it out of the equations entirely. And Einstein and de Sitter basically banished lambda from the discussion. And they thought you'd have a universe that was always expanding, but because of gravity, always slowing down, always decelerating. Like a ball that's launched with escape velocity from the surface, or a satellite that's launched with escape velocity. It would be something that was moving away, slower and slower, but always moving away. That the universe would be expanding, but always decelerating. So if you go to Washington, to the National Academy, and you go to see the Einstein statue, it has some equations on here. Some of you will be familiar with these. E equals mc squared, needs no introduction. Here's the equation for the photoelectric effect. The Craven Swedes gave him the Nobel Prize for that because they didn't know about this relativity stuff, seemed kind of newfangled. And up here is the basic equation for general relativity with no lambda term. Now, when you came in this building, near the wine, there is a wall with lots of equations. And on that wall, John, is this equation with no lambda, if I may say. That's the handwriting on the wall. I'll come back to this. Okay. But, the usual way we tell it this in textbooks is Einstein smacked himself on the forehead, said, well, lambda, terrible idea, forget about that. But it turns out that there were other people who took this quite seriously and who actually had a rather modern view of what lambda might mean. One of these is Georges Lemaitre, who was a Jesuit, a Belgian priest, and who got a PhD from MIT, an unusual combination. And he said, everything happens as though the energy in the vacuum would be different from 0. That is, the vacuum, the empty space, would have some properties. We associate a pressure, P equals minus rho c squared. So there's a negative pressure, a kind of springiness to space itself, to the energy density of the vacuum. This is the meaning of the cosmical constant lambda. This is the way people think about the cosmological constant today, or at least some people. So he's very modern. He's kept with it. He did not join in with the bandwagon of getting rid of the cosmological constant. Here's a cartoon from a Dutch newspaper in 1930. De Sitter had read Lemaitre's work, and it shows De Sitter in the shape of the Greek letter lambda. And here's Dutch. English is a dialect of Frisian. Where's the linguist guy? He'll back me up on this. And you can read it. What blows the ball up? What makes the universe expand or swell up? Opzwelt. That's got to be lambda. No other answer can be given. Also, I have the translation written down here in case I stumble. So this idea was that the lambda, which acts in this kind of anti-gravity way, would make the universe expand. And so here you see the lambda is making the universe opzwelt, swell up, and the galaxies move apart. Well, de Sitter stopped talking about that pretty soon, but Lemaitre did not. Okay. Now, I said I'm here to tell you about this. Why don't I tell you about it? Okay, how have we done it? Well, there are things brighter than Henrietta Leavitt's stars. There are things that are 1,000,000 times brighter than Henrietta Leavitt's stars, and those are the exploding stars we call supernovae. They're thermonuclear explosions. They're 1,000,000 times brighter. The apparent brightness goes like the square, that goes like 1 over the square of the distance. So that means if they're 1,000,000 times brighter, you can see them 1,000 times farther away. The distance to M31, the Andromeda Galaxy, is a few million light years. Democrats controlled both houses of Congress back then. And the distances to the galaxies I'm talking about now will be a few billion light years, 1,000 times farther away, using these supernovae instead of Cepheid variables as the tool for measuring distances. So you might say, this is great. Why didn't people get on this right away? And the answer is the supernovae are quite rare. There's about 1 per century in a galaxy. So if you assign a graduate student, keep an eye on that galaxy, it takes them a long time to finish a thesis, and they won't do it. But here's a supernova in a galaxy, and the trick is somehow to find a way to find the supernovae fast enough. Fritz Zwicky is shown here with the 18-inch Schmidt telescope at Palomar. This was the first of a very novel optical design that allowed you to get a big field of view and to search many galaxies at once to look for supernovae. And he did find some in the 1930s. I knew Fritz when he was at the end of his career, just when I was a graduate student. Fritz worked on a number of things, including the supernovae, including looking at clusters of galaxies where there are many galaxies together, and he was able to analyze the motions of the galaxies, the velocities of the galaxies, and infer the presence of much more matter in clusters than associated with the stars. That is, that there is matter, dark matter, associated with galaxies. And we'll see that a large fraction of the universe is probably in this form, not the luminous stars, not the atoms that we're made of. And here's Fritz at that age. So he's a pioneer in supernovae. He's a pioneer in dark matter. He's also a pioneer in nonverbal communication. He had a very low opinion of his Caltech colleagues. And this is the gesture he called the spherical bastard. He said, you look at them, they're spherical bastards. They're bastards any way you look at them. Sorry, children. Didn't mean to. Okay. So Charlie Kowal's a guy who worked for Fritz at Caltech, and here he is holding the most advanced image technology of 1968, a great big photographic plate from the Palomar Schmidt, the 48-inch Schmidt, which was a bigger telescope than the one that I showed you a second ago. And he did monthly searches in the dark of the moon to look for supernovae back in 1968, and they found many supernovae and began to get the inkling that they could be used for this purpose. This is a modern diagram based on our observations of type 1a supernovae, these exploding white dwarfs. And what's plotted here is the same thing that I plotted in Hubble's Hubble diagram, the velocity going up this way. This is 1/10 of the speed of light. And distance out this way in astronomers' mysterious units, so the physicists will have to ask us, what does that mean? This is about 2 billion light years out across this diagram. And you can see that the velocity is proportional to the distance. The supernovae are very good indicators of an expanding universe of the type I've talked about before. Down here in the lower left corner is a little red square. You can see the Kremlin over here, St. Basil's over here. This is actually the diagram that I showed you before, the region of the diagram I showed you before, of Hubble's Hubble diagram. So he was working really nearby, but he was seeing an effect that's a general one. He also had some data a little farther away. even at the beginning. Okay, so what is the history of cosmic expansion? The idea is to look deep into the past. I said that the light from distant objects takes time to get here, so you look at distant objects, the light takes time to get here, and you find out what the universe was like back then. Here's a picture taken with a CCD, a charge-coupled device, like the things in a digital camera silicon chip, like in a digital camera or in some of your phones, and taken by starlight alone. And what you see here is our galaxy, the Milky Way. This is in Chile. This is our galaxy, the Milky Way. And over here is the large and small Magellanic Clouds. Those are the places where Henrietta Leavitt got the plates, the photographic plates that were taken by the Harvard observers in Peru and found out about this law that enabled people to measure the distances to galaxies. And this, in the middle, is the 4-meter telescope at Cerro Tololo, which was equipped with a very big camera, even in the early 1990s, which was used, among other things, for this investigation. So here's the idea. We live here now, and we look back into the past. And the universe has been getting bigger over time. It's expanding. So that means the graph is going up. From the time of the Big Bang, which we think is about 13.7 billion years ago, the universe is expanding and slowing down, probably, due to the density of matter, which was higher then. And then at some time in the past, maybe, there was a switch over to acceleration, or at least that's one of the possibilities. Now, we're much better at observing the past than at predicting the future. This is why, well, astronomy is not the same as running a quantitative, well, never mind. We're not so good at predicting the future. We don't know enough yet about the properties of the universe to be able to predict precisely what's going on and going to happen in the future. But one possibility is, and I'll show you that this is the one that seems most likely, that there is something like the cosmological constant. If that's true, the expansion of the universe will be literally exponential. That means the rate will be proportional to the size. And as the universe grows bigger, it will expand faster. A horrifying thought that I'll come to at the end. Okay, so I said this was going to have a lot about the advances in technology, and here's one. Here's my thesis advisor, and here's the world's largest silicon detector for light in about 1990. It is 0.24 megapixels, and he's very happy to have it. But as you all know, one of the things that has really changed is the cheapness of computers, the ability to fabricate these computer chips, and these detectors are computer chips. They are silicon chips. So here is a more or less modern one. This is also makes somebody very happy, as you can see, even though he's wearing a mask. And this thing here, which is as big as that photographic plate that I showed you from 1968, is all silicon. Silicon is 100 times more efficient at detecting light, and of course the signal comes out in a digital form so that you can do things with it, like add or subtract images. Okay, so how do you use one of these to find the distant supernovae? It's 1 in 100 years is the rate. That's about they're 50 weeks in a year, give or take, except in France where they take a much longer vacation. But anyway, that's about 50 weeks in a year, so 50 times 100, that's 5,000. So if you look at 5,000 galaxies, your chances of finding a nice fresh supernova are pretty good. So all you need to do is look at 5,000 a night. The graduate students won't do that either. It's disgusting. Anyway, but if you look at this picture, you can see there are lots of galaxies, hundreds of galaxies, but the ones we're really interested in are not the ones that kind of knock your eye out. They're these little tiny ones back here. Most of the galaxies that are far enough away so that the supernovae are halfway back to the Big Bang, 7 billion light years away, are so faint that they just barely show up in this kind of image. So those are the ones you have to find in order to probe the past and see whether the light traveling to you has been traveling through a universe that's expanding at a constant rate, slowing down, in which case the distance will be a little smaller and the supernova will appear a little brighter, or accelerating, in which case the distance will be bigger and the supernova will look fainter. Okay, so here's Brian Schmidt, who was mentioned in the introduction, and he's explaining to his thesis advisor how easy it's going to be to do this. He said, well, there's nothing to it. I can write the software for this. I said, well, there's this other group, the group at Lawrence Berkeley Lab, headed by Saul Perlmutter, and, you know, they've been working on this software for 5 years. And he said, yeah, I know. He said, I can do it in a month. And so it turned out it was youthful arrogance, but it was also true. And in a month, we had very bad software that worked, sort of, to do this problem. Here's the idea. Here's a picture that might be from tonight. This is a little tiny fragment of one of those images. This is about 1/1000th of the image area, in fact. So here's a little picture. And you can put that in a computer. It's a digital image, so there's a number at each location that represents how bright the object is. And you have a picture from last month. These supernovae take about a month to get bright. And you can subtract one from the other. When you do that, the things that stay the same, like this little spiral galaxy, disappear. And the things that were new last night, even if they're hard to see, are left over. So maybe you can see it now that this galaxy has on top of it a little star, which is a supernova inside that galaxy. The month before, there was no supernova. When you do the subtraction, there's a nice little dot left over, and the software puts a red ring around it so you know it's really right. Actually, not the software. It does not do that. Okay, so that's what Brian did. Adam Riess was also a graduate student, and he worked on this idea that the measurement that you get could be misleading. If you're looking at a distant object, it could be dim because it's far away, or it could be dim because there's dust in the way. And there are galaxies there are dust in galaxies. The Milky Way has dust, other galaxies has dust. And Adam worked out how to account for the presence of dust. And that gave us an advantage over the other group, which hadn't learned to do this yet. So here's Adam in 1966. Here's me in 1996, rather. 1996. This is Bill Press, who was also Adam's advisor. And as we like to say in Massachusetts, it's okay to have two daddies. Okay, and here's Adam Riess's notebook from the fall of 1997. He was working on this problem. Adam went to the Massachusetts Institute of Technology as an undergraduate and then to Harvard as a graduate student. At MIT, they teach you to keep a lab notebook. And this is his lab notebook, where he began to stumble onto something funny. He said, well, if there's no cosmological constant, that's what this means, then you have to get negative mass. Maybe you can read this. It says minus 0.36. Mass less than 0. And so he called me up. This was maybe October of 97. And he said, you know, I'm getting this value. And I said, well, you've clearly done something wrong, so do it again. And well, it turned out, Brian also did it. It wasn't wrong. That this was the sign, not that there was negative mass in the universe, but that this assumption that the cosmological constant, this lambda, omega lambda was 0, that was not the right thing, that in fact there is something making the universe speed up. So let me show you the data. Let me speed up and show you the data. So here's from 1998. The data in blue is from our team. The high redshift data from blue is from our team. All the data at low redshift is from our team or our colleagues at Cerro Colón in Chile. But I've colored in red the ones that were used from that sample that were used by the other team. So there are two teams, the high Z team, that's us, the Supernova Cosmology Project, that's Saul Perlmutter's group. We had 50 objects in our sample, they had 60 in theirs. They say, we had a much bigger sample. I don't know quite why that is. Anyway, what you can see in this picture is if the universe were decelerating, the points would lie on this line down here. And, you know, the data's kind of noisy. This looks a little like Hubble's old beginning diagram, but you can see that they don't center around here. The horizontal line is a case where there was as much matter slowing things down as we knew was present in clusters of galaxies, the dark matter that was really present. And that doesn't seem like the right fit either. The points mostly lie up above that. They're a little fainter than they would otherwise be. That's as if the universe was expanding more than you would expected during the time the light was in flight. It's as if the universe is accelerating. And today we have a much bigger sample, over a bigger range in redshift. We have hundreds of objects. And this idea that seemed right back in 1998 really seems right now. Let me just show you what the measurement is. the idea is you have to figure out which of these black lines fits the data by changing how much dark energy there is. This omega lambda says what fraction of the universe is made of the cosmological constant or something like it. It starts at 0. That's too small, too small, too small, too small, too small, too small. Pretty good, pretty good. Oh, stop, please. Go back. Anyway, what you can see is that somewhere about 2/3 of the way through, for values around 0.7 or so, you get a pretty good fit to the data. So that tells us how much dark energy there is in the universe. And now we say easy. It wasn't so easy in 1998. Here's another way to talk about this. This is the real analysis, where you show how much dark energy there is and how much dark matter there is. If you had asked a theorist, if you'd gone up to the world's leading theorist in cosmology and asked them in 1990, where do you think the solution lies? They would all say, right here. But what these contours mean is that the chances are 2 out of 3, 95%, 1 in 200, that it's within this area over here. So we favored a solution which had omega lambda, that is dark energy making things accelerate, whereas the solution that I showed you before, that dashed line that was curving down, correspond to what most people thought would happen. So this was a big surprise, that's fair to say. Then I showed you the 500 points. This is the diagram for the 500 points. First of all, it's a lot smaller. The ellipses are a lot smaller. That means we know a lot better what the properties are. Here's the data for the supernovae. I'll bet you 2 to 1, I'll bet you 20 to 1, I'll bet you 200 to 1 contours for what the supernovae are telling you about the dark energy and the dark matter. When you take the evidence from the supernovae, from how galaxies are clustered, from the glow from the Big Bang, and you put it all together, there's this little gray area in here which is the best solution for all of those, and again, different levels of uncertainty. And so we're pretty sure now that this value is not 0, and this value is not 1. That point's over here, and that's really excluded by the data. Now, there are some very conservative groups in the world, and one of the really conservative groups is the Swedish Academy of Sciences. But they've come around, and they awarded to Saul, to Brian, and to Adam Riess for the discovery of the accelerating expansion of the universe through the observations of distant supernovae, the Nobel Prize from last year. This year, the prize will be next week. I don't know what it'll be about, but it won't be about this. Or as the head of the committee said to me, you'll just have to do something else. Thanks a lot. Okay. So here I am glowing, as you can see, with pride, in the lobby of the Grand Hotel. The guys forgot to wear their badges. Brian is a graduate in 93. He got his PhD in 93. Adam got his in 96. Okay, ha ha. And the other thing is, the symbol for cosmic deceleration is Q0. This symbol that we use that tells how the universe is slowing down. And Adam was nice enough to make all of us a set of cufflinks, which I am wearing today, that say Q0 is less than 0, which to the cognoscenti means the universe is accelerating. And they're solid silver. It's really great. Okay, whoops. All right, so what's the universe made of? Well, it's mostly this stuff that's making the universe expand faster, which we call the dark energy. It might be the cosmological constant, it might not. The dark matter, turns out there are many good reasons to think it's not made of the atoms that we are. So it's not made of neutrons and protons. It's probably made of something more like neutrinos, but massive, that we call the cold dark matter. So the universe that we see and that we know is made up of atoms. All the galaxies, all the stars, all the planets, all the people, everything we love is made up of atoms. And that is just a small fraction of the stuff in the universe. The history of the universe and the future of the universe will be determined by the properties of the dark energy and the dark matter. So there's a kind of tug of war taking place between these invisible things, and the matter is just on the surface kind of following the instructions of either slowing down due to dark matter or speeding up due to dark energy. People are very proud of this diagram, I must say. They say, look, our diagram is full. And it's very important, especially for the students, to ask, what is it full of? And in this case, it is full of our most important asset, ignorance. We don't know what the dark energy is. You've already caught on to that. And I've been so vague, you know that we don't really know what the dark matter is. So that means for the young people in the room, there's plenty to do. 96% of the universe is not understood. Really important to get to work on this. Okay. But what about the theory? Now, I have this very fine International Brotherhood of Theorists card, which signed by a Nobel Prize winner, valid to infinity. It's the best thing that Photoshop can make. That gives me the authority to talk on this subject. And usually a theorist will do a calculation on the back of an envelope, and here it is. And if they do, and they try to estimate the energy of the vacuum that's associated with gravity, they can do it. And they get a number, they get a number that is about 10 to the 120th, where the correct value is 0.7. This is what we refer to in academic circles as not good quantitative agreement. What other people would say is wrong. There's something missing. We don't understand how to do this problem right. There's something missing to our understanding of gravity right at the point where it intersects with quantum mechanics. This is not news. We've known that there's a problem for a long time, but this is one more manifestation of it. Another possibility is, of course, that the dark energy is something that's not a constant, like the cosmological constant, and there are fields that people have proposed that might do that. There also could be modifications to gravity. General relativity is a theory that was invented by an extremely brilliant person in 1916, and it has passed every test to which it's been subjected, but that doesn't mean it's perfect or will never be supplanted. Maybe this is something that's showing us that the limitations of general relativity. We don't know which of these is the correct way to think about it. You can try to see if the dark energy is the cosmological constant or not, but you can't tell decisively just from this expansion history, this sort of thing I've been talking about tonight. You also need other information about how structure has grown in the universe. And people are thinking very hard about how to do that. So one idea is maybe you could put this lambda on the right-hand side of Einstein's equations, that there would be some energy associated with the vacuum. And I thought of doing that and started to do it at the Einstein statue in Washington, but the park police came by. And I was just thinking, here it might not be so difficult, because I think I could reach over there with a marker and maybe put that in. But maybe I won't do it. But I understand you're going to have this carved in stone. Well, that's pretty presumptuous. Anyway, we'll see. All right, so maybe a metaphor will help. I said that the universe is made up of these two things, the dark matter and the dark energy, that the dark matter makes up most of the galaxies. But what we see is the light from the stars. Here's the metaphor. What you see is the snow. But the snow is not the mountain, grasshopper. The snow is not the mountain. Or here. I said that, the thing that's propelling the universe outward is this dark energy, but we don't see the dark energy. But you're used to this sort of thing of inferring invisible causes from the effects that they produce. So here's a painting that shows, wait a minute, wait, that shows trees blowing, and you ask somebody, well, what's making the tree move? And they'll tell you, it's the wind. You don't see the wind. You see the effects of the wind. You see the tree moving. And in the same way, we see the expansion of the universe. We infer the presence of this dark energy. So it's not as mysterious as sometimes people say. But it's pretty mysterious, and if you want to learn more about it, I couldn't recommend a better book than this one, available from Princeton University Press and shipped right away from Amazon. Okay, let me just say a couple of words about the future. I always thought that the future would get here sooner, and that somehow we'd have anti-gravity boots, and maybe this dark energy could be applied for that. No, that doesn't seem to be in the cards. But I want to say a word about measurements that we'll do in the not too distant future that are going to be better and are going to tell us more about whether the dark energy is the cosmological constant or not. This dust that I mentioned before really is a serious problem. Adam made some progress on it. But it turns out that the dust is almost transparent if you go to longer wavelengths, out into the infrared. and we're beating our head against the wall. The biggest uncertainties come from dust. This picture was at a website about the theft of intellectual property, and they said, you're beating your head against the wall. So I stole it, because I thought it would kind of be appropriate in this context. Now, you can see through the dirt by going to longer wavelengths. This is a little obscure, but this is at visual wavelengths. You can see this silhouetted, this blob of dirt silhouetted against the stars of the Milky Way. But as you go to longer and longer wavelengths, which are shown this way, at 1 micron out to 2 microns, the visible light is at half a micron wavelength, you see that the dust becomes transparent. You can actually see through it. So if dust is the problem, why not make the observations in the infrared? And that's the avenue that I'm pursuing right now. We're using the big detector that John Tonry is shown with here at this telescope on Haleakala and on Maui. It takes a picture of 7 square degrees all at once. The moon is half a degree across, so there'd be like, 100 moons. And it has lots of galaxies on it that have lots of supernovae in them that we can find by these digital techniques that I described earlier. And the idea is to pick out some of those and then make infrared measurements above the Earth's atmosphere using the Hubble Space Telescope. So we have a program to do that. It starts in October. Oh, it is October. Maybe we should be doing it tonight. Oh, it's so exciting. I don't know. So anyway, we'll see how that goes. Thinking ahead, there are going to be things more powerful than that Pan-STARRS telescope. People at Brookhaven are intimately involved in building the camera for the Large Synoptic Survey Telescope, which is the big ground-based project that's going forward in the coming decade. And it will be a much more powerful system for this kind of thing. It could work in tandem with the telescope that will be in space at that time, the JWST, the James Webb Space Telescope, which is an infrared space telescope, and that's what's coming in the future. What I'd really like to build is a big ground-based telescope that could outperform the Hubble Space Telescope, and we are on the path to do that. We're building the thing we call the Giant Magellan Telescope. It's in Chile. It will have 7 mirrors, 6 of which are around the edge and 1 in the middle. If we get this thing built, it'll have 100 times the collecting area of the Space Telescope, so much more light. And if we can correct for the Earth's atmosphere, which we're learning to do through adaptive optics, it'll have 10 times sharper images. And this will make it possible to make these infrared measurements from the ground. So we're really looking forward to that. I just show you a supernova in a galaxy for a nearby one. Whoops. For a distant one, the light from the galaxy and the supernova are all blurred together. Space telescope is great because it has the angular resolution that separates those. And this big telescope that we're talking about, here's a space telescope image of a galaxy and a galaxy with a supernova, a galaxy, a spiral galaxy, and a spiral galaxy with a supernova. What you'll be able to do, this is the size of the supernova image from the ground. This is what you get with space telescope. That's a fairly good representation of it. With this Giant Magellan Telescope, using adaptive optics, so taking out the blurring of the atmosphere, the image ought to be that size. So measuring the brightness of the supernova in the presence of the galaxy should go a lot better. Okay, well, that's enough. Except to say we're really building this thing. Here is an 8.4 meter mirror, which is under the football stadium at the University of Arizona. We've made one, and we've figured the front of it properly. It seems to be good. And the second one has already been cast. So we're on this path. We don't quite have enough money to get to the end, but we're working on it. Okay, so what kind of science is this? Well, this is a university. We like to go to the high-tone sort of philosophical stuff. And Socrates, let's see. Socrates didn't publish it much, but he had good graduate students. It was all right. Socrates says, shall we make astronomy the next study? What do you say? And his stooge, Glaucon, says, why, certainly. A working knowledge of the seasons, months, and years is beneficial to everyone, to commanders as well as to farmers and sailors. Socrates says, you make me smile, Glaucon. You are so afraid that the public will accuse you of recommending unprofitable studies. I think we should do this even though it's not for profit. Because people are interested in the big questions. People are interested in where we came from, where we are, where we're going. And just as Gauguin tried to allude to those kind of mystic questions in this painting, we're taking a scientific approach to try to answer the same sorts of questions. So even though this is unprofitable, I think it is an important thing for people to do. Thank you very much.
Have time for a few questions.
That depends how long the answers are. Sir,
Yeah, I was curious.
are you from the American Institute of Physics?
Indeed I am.
I'd like to thank you for that fine prize. Go ahead.
You mentioned earlier that you made the assumption that if something was brighter, it was further away, or brighter, it was closer.
Yeah.
How do you know that the thing itself is not dimmer or brighter?
Sure, good question. So these supernovae, of course, are not machines, you know, they are natural events, and there is some range in their brightness. We know from looking at objects that are at the same redshift, that you think are at the same distance, how much they differ from one another. So we can measure that effect. We can also look at that nearby and far away and see whether that scatter gets bigger, which it doesn't. We can see whether the velocities in the atmosphere of the explosion itself are the same or different. They're the same. We can see whether the chemistry is the same, the colors are the same, and so on. So we don't have proof that the distant ones are identical to the nearby ones, but all the circumstantial evidence points to the events being similar at high redshift and at low. But as we try to make more and more precise measurements of the properties of the dark energy, these subtle effects might become more important. One thing that I didn't mention about the near-infrared, but which I'll mention at the technical talk tomorrow, is that the supernovae are more nearly standard candles when you observe them in the infrared. So it's not just that the dust is less of a problem, the supernovae behave better. It's nature's way of telling you what to do. Yeah?
When you say that the universe is expanding, do you mean that galaxies and such are expanding within space, or that space itself is expanding?
Yeah, I mean the second thing. So the question is, when we talk about the expanding universe, do we mean that the galaxies are getting bigger, the way it was in my picture, or whether the space between them is getting bigger, which is really what we do mean. That the idea is if you had 3 points, never mind galaxies, in space, and you could measure over time how far apart they were, that triangle would grow bigger. That's what I mean by expanding. I do not mean that there's some edge to the universe and it's moving outward. And I don't mean that it's just the simple-minded thing that I showed in that animation, which you have now exposed as fundamentally flawed. And now I'll have to decide whether to ever show it again. It's not your fault. Yes?
You mentioned that theoretical estimate based on the idea that dark energy is cosmological constant is often 120 orders of magnitude.
Yeah.
But isn't cosmological constant itself a purely adjustable parameter?
That's what some people say. So if you talk to highbrow theorists who think about this stuff, they say, well, we have no explanation. Maybe there is not just one universe, but there are many, like 10 to the 500, and that these different universes all have different values of the physical constants, including the cosmological constant. The ones that have big values for the cosmological constant accelerate away in the first second. Galaxies never form. Stars never form. Heavy elements like the iron in your blood and the calcium in your bones don't get made by supernovae. There are no people to study those universes. So the fact that we're here tells us we must be in a universe, that has a small value for the cosmological constant. This kind of arguing, so-called anthropic reasoning, seems like cheating to me, but I would say at the moment that's the leading interpretation of this. Not that people have really predicted the cosmological constant or the energy associated with the vacuum, but that they say, well, it must be small, otherwise we wouldn't be here asking this question. It seems kind of I think physics should do better than that. We should really predict it. But, for the moment, that's more or less where it stands. So it shows this is a very important problem and that there's a big area of not understanding. Yes?
Are you able to see, like, if you're on the moon, can you see, like, the lights in New York City, like, people's, like...
If you were on the moon, could you see the lights in New York City?
Yeah, like...
With a telescope, you mean? Or with your naked eye? What is your question exactly? Could we measure the lights from New York City? Oh, yeah.
No, I mean...
We can measure a candle on the moon. We can measure a match on the moon. Excuse me. I didn't mean to raise my voice. Big telescopes can see something that's the equivalent of a candle on the moon. Flash bulb. No problem. So, but looking back the other way, no, if you look at the Earth from space, have you seen that picture maybe of the Earth from space? You can see that the areas of population are quite bright, and yes, you would see them. You could probably see this from the outer solar system too, if you happen to be living out there. We don't believe anyone is. Yes?
We exist in a very mass-dense environment compared to intergalactic space.
Yeah.
I'm curious if there are any theories about whether particles do something different in that environment than they do here, even though you're extrapolating.
Oh, well, it's a good question. I mean, we do live in a very unusual place, and that's why our common sense, which is mostly derived from things like catching baseballs and so on, not always a complete guide to cosmology. But the question of whether at extreme densities, much lower than in any terrestrial laboratory, the laws of physics are somewhat different than they are, at high density or high gravitational field, is an interesting one. So one suggested alternative to the discussion of dark matter is that the laws of physics, of gravitational physics, or the way a force produces an acceleration from gravity, is different for very low accelerations, the kind that correspond to the rotation of galaxies or the motion of stars in clusters. So that at least has been, that kind of idea has been suggested, that the things that are beyond the measurement in the laboratory might actually have different rules, and as a result, we're misinterpreting the data. That picture doesn't seem to have prevailed, but people certainly have brought it up. Yes?
Can you say something about the impact of the discovery of the Higgs?
Yeah. So the question is, what about the Higgs? What does that tell you? Well, it's very interesting, because one of the ideas for the dark matter has been that it would be the lightest of these supersymmetric particles, another idea in particle physics. And the fact that there is no signature yet of these supersymmetric particles in the energy range that has been searched so intensively for the Higgs is somewhat embarrassing to the people who thought about this theory, because having a particle of that mass would be just right for explaining the dark matter. And at least as far as I know, there's no sign of that in the particle stuff. The Higgs particle itself is kind of interesting, because it would be the signature of an underlying field, the Higgs field, and the discussion of the very early universe in terms of inflation also invokes a theory of that general type that has a field that changes with time in it. And it could be that the acceleration that we're seeing today is also somehow related to that kind of mechanism, a scalar field, as it's called in the trade. So I would say the Higgs gives a kind of decency to talking about scalar fields, but the other evidence from the LHC does not make it simple to think about this lightest supersymmetric particle, the thing that everybody, no one has ever seen this particle, but it has a name, the neutralino. Cute name. But that doesn't mean it's real. Yes?
Just a historical question. If I remember it correctly, I might be wrong. In the later years of his career, Dirac, based on some strange arguments which nobody took seriously, was actually led to believe in the relevance of this lambda term in Einstein's equation.
Yeah.
is that
I don't think anybody's gone back down that path.
right? But
I mean, people have gotten older, but they haven't gone on the same way that Dirac has.
believe in the relevance.
I don't know. I don't think anybody takes that seriously, but maybe it's worth looking at it. I don't know. I'll tell you what my impression is of the theoretical state, which is that it's a weedy garden. There are a lot of ideas, none of which seems compelling for what the dark energy might be, and that the empirical way forward of measuring the properties of the dark energy, which I'll talk about a little bit tomorrow in the technical talk, is quite limited in what we're going to be able to do over the next 10 or 20 years. We'll be able to tell if the cosmological constant is or is not the same as the dark energy to maybe a few percent. But measuring the change over time that might be related to one of these fields, scalar fields that's changing, that'll be really hard. And what I think is missing is a really good theoretical idea, a really compelling theoretical idea that would tell us how good the measurement has to be and sort of which aspects of it would be most sensitive. So in the case of the Higgs, there was a very good prediction. You know, there got to be, after decades, there got to be a very good prediction of sort of what to look for. And so when people focused the search on that problem, you know, that was a very successful technique.
Let's take one more question.
Yes. Go ahead.
So, let's be pessimists and say that there's something wrong with all of this.
Oh, gee.
What would your top guesses be as to major causes of what could be wrong with all of this?
Yeah. I think we're beyond the point where it's something where the supernovae or the dust is causing an effect that's big enough to delude us. The matrix of evidence from different, completely independent lines of reasoning seems pretty good that there must be something that looks like cosmic acceleration. But these things that I mentioned about changes in general relativity, where, you know, Einstein's idea is an extremely good one, and it's very hard to do better than he did on these matters, but, you know, it could be that that's part of the story, that on some very large length scales, the story that underpins general relativity is just not right in some way that we don't understand at the moment. That's a possibility, I guess, that would be kind of exciting if that were true. I mean, it would be the first kind of improvement in 100 years on this theory. But it's not so easy to do that. You know, there are many constraints on for precision tests of general relativity that have been done. You know, starting in Einstein's time with the precession of Mercury and many other things that people have done since. So I don't know. You know, I'm just an observer. I call him as I see him, or as I think I see him, which I forget which is more important. Anyway, you know.
Let's thank Professor Kirshner again.